one of the most basic things you can ask about a number is whether or not it's positive or negative. So sign analysis is determining when an expression is that. So it's pretty simple. So sign analysis is this procedure which involves, as I said, determining when an expression which represents a number is positive or negative. So what I want to do is to think about some simple examples first. So I'm not going to give a completely general picture for how to do this. Really, you need to wait a little bit until you've done calculus to come up with a really systematic way to deal with lots of different expressions. But there are certain types of expressions that you will see before you do calculus that it's important to determine if they're positive or negative. So let's do some simple examples. Let's do the following examples. So let's do two linear expressions in x. So imagine I have 2x plus 3. And I ask myself, is this positive, or when is it positive? When is it 0? When is it negative, let's say? So when is it positive? 2x plus 3 is greater than 0. So this is if and only if. Well, if we take away 3 from both sides, that preserves the inequality. So I get 2x is strictly greater than minus 3. And then I can divide through by 2 or multiply through by a half, and that preserves the inequality because a half is positive. So I would get x is strictly greater than minus 3 over 2. So here, the crucial thing is that, well, it's up to you how you do it, but 2 is positive. So this implies the inequality is preserved. Inequality is preserved. Okay. So being strictly greater than 0 is exactly the same as x being strictly bigger than minus 3 over 2. Okay, what about less than 0? So if it's strictly less than 0, we'd have 2x plus 3 strictly less than 0. Basically exactly the same logic. 2x would have to be strictly less than minus 3. And then you'd multiply everything through by a half, and half is positive, so it preserves the inequality, so just exactly the same deal. So x is strictly less than minus 3 over 2. Okay. And of course, the central position to this would be if 2x plus 3 is equal to 0. And then by the standard pieces of algebra we've seen many times now, this is if and only if x is equal to minus 3 over 2. So let's kind of gather this together into one reasonably easy to understand format. So I think it's good to think visually about this. So we're really asking about where on the number line 2x plus 3 is positive and where it's negative. So it makes sense to draw a number line and to come up with a way to describe what the values are. So what we're going to do is the following. We're going to mark the positions here where it's 0. That seems sensible because it seems like kind of an important point. So at minus 3 over 2, that's an important place to mark. So this is exactly the position where, it's the position where my expression 2x plus 3 is equal to 0. Okay, so what do I see? Well, I'm positive if x is strictly bigger than this. So let's represent that with just a plus on this side. So let's attempt it anyway. And I'm negative if I'm strictly less than it. So on this side, I'm negative. And I know that's true forever in both directions. So this is a really nice, succinct way of describing what the behavior of the function is in terms of sign, positive or negative. So for example, just to hammer home this point, I mean, this is exactly the statement over here that for x, here, the expression 2x plus 3 is negative. So that's what this is shorthand for, this kind of minus sitting above it. The other side, positive. Okay, let's do another example. That was very simple because, well, it's an extremely simple expression into x. It gets more complicated if I have more complicated expression. So let's do one that's very similar looking but a little bit different. So let's do 1 minus 2x. And let's go through exactly the same logic, shall we? Okay, so 1 minus 2x greater than 0. When does that happen? Okay, so this is if and only if. Let's take away 1 from both sides. So minus 2x is greater than minus 1. Remember, adding and taking away doesn't change the inequality direction. But now, in order to get x on its own, I'm going to have to divide through by minus 2. So that's the same as multiplying by minus a half, and multiplying by a negative reverses the inequality. So this is if and only if x is strictly less than minus 1 divided by minus 2, which is equal to a half. Okay, so very important. Above the 2, so this is not very well written, this 2 is positive, but now below it's a minus 2 I'm dealing with. So at this point, minus 2 is negative, which implies the inequality is reversed. Okay, right, so what about the other side? So the other side, minus 1 over 2x less than 0. If and only if, same story, minus 2x less than minus 1, but then I've got the same exact deal. So now I'm going to divide through by minus 2, but that's going to flip the direction. So it's kind of backwards to what I see above. And then, of course, bang in the center, 1 minus 2x, if and only if x is equal to a half. So putting all this together, what do I have? Well, let me draw exactly the same basic number line. And this key moment is a half in this case. But now it's kind of the opposite way round. So the opposite way round in the sense that it's positive x is strictly less than negative, or a half, sorry. And it's negative if x is strictly greater than a half. So it's kind of backwards to what you'd expect. Right? It flips it. It's not how the usual orientation of plus and minus goes. And again, as above, this half is exactly the solution to 1 minus 2x is equal to 0. Okay. So you can see here linear expressions are fairly easy to deal with algebraically, but there are a little bit of subtleties going on because, I mean, the coefficient in front of x, the sign of that seems to dictate something important, right? So if the coefficient was 2, like in the first example, it switches from negative to positive as you move from right to left. But if it's minus 2, so negative, it switches. It switches from positive to negative as you move from left to right. So this is part of a more general story. And I think I'm going to kind of give you the general picture here, just written down. I do want to stress, you shouldn't sit down and just memorize this, what I'm going to write down. You should take the time to really understand why it's true. Memorizing has its place, but not when you're doing things like this. You need to really understand the meaning of what's going on and why things are true, because you won't be able to retain the information if you don't. And this information is so crucial to so many things later on. If you don't have it really internalized, it's going to kind of cause problems which compound and compound until eventually it's going to be very difficult to make any progress. So more generally, the following is true. More generally. So if I take an expression, a linear expression, ax plus b, all right? And let's go a little bit more general on this as well. Let's imagine raising this to the power of a whole number. So something like this. So a and b are constants, and let's assume a is non-zero, shall we? Otherwise this is kind of silly because it would just be a constant. And let's say n is a whole number. Could be 0, could be negative, doesn't matter. Whole number. So in more fancy terminology, that's an integer. Now, I know a few things. I know if I take some number and raise it to an even power, it's always going to be positive. I know that if I take a number and raise it to an odd power, then the sign will depend on the number I start with. For example, minus 1 squared, it's positive, but minus 1 cubed is negative. So I think I need to separate my story into n is odd and n is even. So n is odd, so we'll do n is even up here. In fact, let's make it a bit smaller. So n even. And then let's break it down below into n odd. Now, for n odd, let's take a little moment to think about this. If I give you a number and raise it to the power 3, and I tell you it's odd, I tell you it's negative. So if I said r to the power 3 is a negative number, what would that mean about r? Well, the only possible answer would be that r is negative as well. So an odd power of a negative number has to be negative. So what this really means is, if I'm in the odd scenario, the sign is going to be completely dictated by this internal expression. If that's negative, then so is the power. So minus 1 is negative, minus 1 to the power 3 is negative. If this is positive, then the power is positive, of course, because if you add a number to itself, or multiply a number by a positive number by itself, it's always positive. So in the odd case, the kind of sign analysis is only going to be dependent on what's going on inside, and we've just seen above there are kind of two possibilities, I think, depending on whether or not A is positive or negative. So let's break this into kind of 3 number lines, and I should, like I said here, I'm going to break this into 2 pieces. So let's break it into one where A is positive and one where A is negative. So for the even case, let's take a moment to think about the even case. So let's draw a number line and think about what the story was. Well, what seems to happen is the most important thing is, well, the starting point is the 0. So ax plus b is 0. That happens at the position what? Minus b divided by a. So this is exactly the position where ax plus b is equal to 0. Very simple algebra. So then what? Well, that would be the position where the expression is 0. What about on either side? Well, if n is even, it doesn't matter what ax plus b is. Raising anything to an even power is always positive. Right? 1 squared minus 1 squared, they're all the same. It's all positive. So in this case, if I was raising it to an even power, it's simple. It's plus on both sides. And when I say plus here, I mean strictly greater than 0. Right? You're 0 at minus b over a, but on either side, you're strictly greater than 0. And what about down below? Well, exactly as I said a moment ago, if you have an odd power, then the sign of the odd power is the sign of the base. It's the sign of ax plus b. So really all we're doing is worrying about the sign of ax plus b here. So again, same story. You've got minus b over a. That's the 0 position. And now what? Well, if a is positive, you essentially fall into the first camp. So you are negative on this side and positive on this side. And again, this is because ax plus b is, for example, negative here. But then if I raise it to an odd power, it's negative. Minus 1 to the power 3 is minus 1, so negative. And then finally, well, we've got basically the same thing for negative, except it's flipped, just like in our second example. Exactly the same basic idea. So that is a kind of a complete story, if you want, for expressions of the form ax plus b to the power n, where n is a whole number. Now again, as I said, you shouldn't just be sitting and memorizing this chart. Absolutely not. You should be thinking carefully about why it's true when it comes down to it. It's a very good exercise. The main thing is, if I didn't have the n, If n was just equal to 1, for example, I would just end up with, it's just this story here. So really this is just the ax plus b story, but when I raise it to a power n, I get a little bit more information going on. So the trick here is to really understand what's going on, not to try to memorize this chart. So this is pretty useful. I've seen lots of expressions already which involve terms like this. What about if I have more complicated expressions? So here's kind of just a general piece of advice about more complicated expressions, so a general strategy. So this is very broad, a general strategy to deal with more complicated expressions. So this basically corresponds to scenarios where you have expressions where you can break them into products and quotients of simple pieces like the ones I've just described. So for these more complicated expressions, what we do is we analyze kind of the simple factors one at a time, and then gather the information at the end. Gather the information at the end. Now I think this is a good example of doing something. Well, we should definitely do this by example. So let me give you one which I think is quite difficult. Well, not too difficult, kind of representative of the kind of thing you might see in some early courses, but let's do it. So here's a nice question. So when is x plus 2 divided by x minus 3 all cubed greater than or equal to 0? Okay, so I can see immediately this is about sign analysis because I'm asking when an expression is greater than or equal to 0. So I'm asking for two things really. I'm asking when is it equal to 0 and when is it positive. So I'm going to have to work out when it's positive, when it's negative, and when it's equal to 0. Now I can see this is a ratio of two fairly simple pieces. One is x plus 2 in the numerator, and then this power of a linear piece, x minus 3 to the power 3, in the denominator. So it makes sense to analyze both of these separately first. So let's do this. Let's analyze x plus 2. So x plus 2, so maybe I shouldn't do an underline in case you think it's on top of something. So x plus 2, well, this falls into, so I'll do this quite quickly, but this falls into this camp, doesn't it, right? So it's linear. The a is positive. The 0 is at minus 2. So x plus 2 is equal to 0 if and only if x is equal to minus 2, just adding minus 2 to both sides. And then what does it do? Well, it goes from positive to negative. Or sorry, it goes from negative to positive. So that's the setup for this. Let's do the second one. So, or the one of the denominators. So this is of the form x minus 3 to the power 3. This is one of my kind of standard cases I've just looked at above. So what does this look like? Well, it's the same basic shape. First of all, the a is positive, so it's going to go from negative to positive when I go from left to right. Let's get this right. And where's the kind of the switch point? The switch point is going to be at 3, isn't it? Which is over here, roughly. So this corresponds, of course, to the point where x minus 3 is equal to 0, which of course is if and only if x is equal to 3, adding 3 to both sides. So now, on the left of 3, you're negative, and on the right, you're positive. Now, what happens when I think about the ratio of these two terms? So let's think about now the full expression. X plus 2 divided by x minus 3 cubed. What happens here? So I want to draw a number line and mark on it where it's positive and where it's negative, and hopefully where it's 0. So I can see above there are kind of two really important points worth singling out. There's the minus 2 and there's the 3. Now, let's think on either side of these what's going on. So over here, what's happening? Well, I'm taking a ratio of two things, one of which is up here, one of which is here. Well, the x is over here. And what does that mean? Well, if I'm on this side, it's a negative over a negative, isn't it? So negative over negative, and a negative over a negative is a positive. Interesting. Now, if I'm between -2 and 3, it would be a positive now divided by a negative, which of course is negative. And finally, if I'm bigger than 3, it's a positive divided by a positive, which is positive. So I can see the sign here. I can see if x is strictly less than 2, you are strictly positive, or you are positive. If it's strictly between -2 and 3, you're negative. And if you are strictly bigger than 3, you're positive. Now, something to say here is, some of you may have seen this in high school, where you have kind of products and quotients of things, and you look at it and you say to yourself, okay, what are the possibilities? It's positive over positive or negative over negative. I will kind of check when these two things happen and go through it. There's nothing fundamentally wrong with that, except the moment you have really complicated expressions, so where you have maybe 5 terms on top and 4 terms on the bottom, then you'd have to go through every single possibility of, okay, this one could be plus, this could be minus, that could be plus, and it turns into this nightmarish mess where you have to kind of check so many cases you kind of lose track of everything. So that approach of just thinking negative over negative or positive over positive is only going to be reasonable if I have a simple expression on top and a simple expression on bottom. If you have something more complicated, it's going to become just impossible. So that's the reason I've done this, is because I've not had to kind of single out the negative over negative, positive over positive. I've analysed each factor, and then I just carefully thought, well, what happens when I take the ratio? And of course, in the wash, I get the negative over negative and the positive over positive. That kind of comes out at the end. But I wasn't thinking about those ahead of time. I was just carefully analysing the simple pieces. Now, this is another thing that I think is different about university mathematics versus high school mathematics. In university mathematics, you're looking for general principles which work, right, across the board. You're looking for kind of a very broad understanding of things and methods which will be applicable to lots of different cases, not just very specific ones. In high school, almost always the cases you look at are incredibly restrictive. So sign analysis, for example, once you've done a little bit more calculus, you'll see how to do sign analysis on expressions which are much more complicated than this. And the method you've learned at school probably would just completely fail. So this is something to be aware of. Many of the methods you have seen already are, generally speaking, highly restrictive at high school. So this is a big shift in perspective. You want methods which can capture a huge number of cases and not just incredibly special cases like you'd see at high school. So this is pretty cool. This gives us the sign, but what am I looking for? I'm looking for greater than or equal to 0. So it's not just when you're positive, it's also when you're equal to 0. So when does that happen? Now let's be super duper careful here. So the only potential locations where this can happen would be here or here. This is the only option. So what I should really do is just check this to see what happens. Now, of course, at -2, if I feed -2 in, I get 0 divided by something non-zero, so I get 0. So at this point, the expression is equal to 0. Fantastic. What about 3? Now be very careful here. 3 is a 0 for that. Okay, it's a 0, but it's for the denominator. So that means you're going to be dividing through by 0. So at this point, you're undefined. The expression doesn't make sense. So let's kind of gather all this together. We've kind of completely determined everything we need to know now to solve this problem. So the conclusion is the following. Conclusion: x plus 2 divided by x minus 3 cubed greater than or equal to 0. This is if and only if. Okay, what are the options? If and only if x is in... Okay, there are 2 positions it can be in, basically, right? So let me just hammer home this point. You could be over here and inclusive of this because you're negative. Or you could be over, what am I doing? You could be over here, but not inclusive of 3 because you can't divide through by 0, remember? So like that. So those are the options. So you're in one of those two camps, so we need to kind of talk about both of them. So this is either in minus infinity to minus 2 inclusive of minus 2, or 3 not inclusive onwards. So moral of the story, check these simple factors and carefully gather the information in a manner like this. Okay, so let's kind of really capture systematically how to do these types of problems, at least at this pre-calculus stage. So here's a more systematic way to do this, because this is, I mean, if I have lots of expressions, it's going to kind of fill up fast. We want a good way to kind of order this information. So more systematic. Okay, so I'm going to do 4 steps, I think. 4 steps which capture how you deal with these types of problems in general, and I'll do a running example down the right-hand side. So first of all, imagine you're trying to do sign analysis, so determining when things are positive or negative for some expression. So the first thing you should do is factor the expression into simple products and quotients. Into product, or indeed quotient, of simple pieces. Of simple terms. Now this obviously isn't completely general, because I could give you an expression where you can't factor it at all. And in that case, in order to do sign analysis, you'll need more sophisticated tools, ones that you're going to learn in calculus. But at this stage, the types of expressions we're going to look at can be factored into simple pieces. So let's do it by example. Let's choose one that looks pretty unpleasant. Let's do the following expression. Let's do x plus 1 to the power, multiplied by 2 to the x, divided by x minus 2, multiplied by x minus 4 there on the bottom. Now, first off, I would imagine many of you have done sign analysis, have only ever done sign analysis with rational expressions. Now, this is not a rational expression, right? This guy here messes everything up. That's an exponent. So you can't just do the standard thing. You're going to have to think more carefully. Now, the x squared minus 4 on the bottom is a bit of a pain. It's a quadratic, but it is a difference of 2 squares. And if I factor that out, I can actually simplify this a little bit to the following. So I'm trying to put this in a form where every piece is very, very straightforward. So when I do the difference of 2 squares, I get an x minus 2 occurring, but there's 2 of them now, and that would be an x plus 2. Okay, that's the first piece. So break it into simple pieces. So from my perspective, there are 4 simple pieces here. There's this, 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 and this. Right. Now, this is exactly the situation where you don't want to do what I described before, this business of going through all the possibles of plus, minus, minus, plus. What are all the options? You don't want to do that, right? There's so many options. You have a plus minus choice there, a plus minus choice there, a plus minus choice there, a plus minus choice there. So that's 2 choices for this, 2 choices for this, 2 choices for this, 2 choices for this. That gives you in total 2 times 2 times 2 times 2, 16 options. So you really don't want to be going through every one of those cases. It'll be incredibly confusing. We need a much more elegant way to go through all the options. So the second thing I'll do is the following. We know in these simple terms, we want to work out the signs, don't we? And we know that what seems to happen is you switch sign, minus to plus or plus to minus, when you go through zeros, or maybe points where things aren't defined. So find all positions where the factors are 0, or maybe undefined. I'll tell you why you want undefined, because you could switch sign by something nasty happening. If I take something like 1 divided by x, you're not defined at 0, but if x is positive, 1 over x is positive, and if x is negative, 1 over x is negative. So you can kind of change sign if you want at positions where things aren't defined. Now, thankfully, in this case, none of that happens. The places where these simple factors are 0 is exactly 0, or simple factors are going to be like this, is only at 0. So the first one, x plus 1, is equal to 0 if and only if x is equal to minus 1, very simple piece of algebra. 2 to the x, so this is a good one, right? What you shouldn't do here is set this equal to 0 and then start doing algebra. You shouldn't do that because you should understand that it doesn't matter what x you choose. This is always greater than or equal to 0. Right? 2 is greater than 0. So by definition of exponents, 2 to the x is always strictly bigger than 0. So this implies 2 to the x is never 0. Okay, it's never ever 0. So what this means is it's always got to be positive or negative. And we can see here it's always positive. Right? Absolutely always positive. So that's kind of an interesting case because you maybe aren't used to dealing with exponents when doing sign analysis. But thankfully, 2 to the x doesn't really affect too much. Next, x minus 2. I suppose I could do x minus 2 squared. That'd be clever, but I mean, maybe I'll just do it. And this is if and only if, of course, x minus 2 is equal to 0. This is if and only if x is equal to 2. All right. And then finally, the other piece is x plus 2 is equal to 0 if and only if x is equal to minus 2. Okay, so it strikes me there are 3 really critical positions that I need to worry about. Minus 1, 2, and minus 2. These are the locations of interest to me. So now, let's do the following. Let's draw a table. So I'll show you what I mean by this in a sec. So draw a table and catalogue the signs of the factors between these points. Catalogue the signs of the factors between the points. Points in 2, the ones we've just found. Okay, so let's do this. 3. Right, so let me shrink this down a bit so we've got more room to play. So what have we got? Well, I'm going to draw a table like this. In fact, no, what I'm going to do is this. I'm going to draw a number line on top. That's going to be the top if you want. And then what I'm going to do is let me mark the positions of interest. So we've got minus 2. We've got minus 1, is that right? And we've got 2 over here. So mark those. They don't need to be relatively in the correct positions, but let's just put them there. All right, so next, just over here, let's maybe draw a vertical line underneath. And what I'm going to do is I'm going to write each of my simple factors as a column. So we'll do x plus 1, we'll do 2 to the x, we'll do x minus 2 squared, and then we'll do x plus 2. Now what I'm going to do is the following. I'm going to mark what their signs are at each of these different positions above. And I'm going to do it between all the intervals. So first of all, minus 1, so x plus 1. X plus 1 is 0 here, and it's going to be negative on this side and positive. So let me write that down as follows. I'm going to write it's negative here, then it's going to be negative here, but then it's going to switch to positive, positive. So I'm going to put 4 things down because there are 4 kind of regions to consider now. Next, 2 to the x is positive everywhere. Brilliant. Just put positive all the way along. Next, x minus 2 all squared. It's a square, right? So it's always positive. Next, x plus 2. Well, it is 0 at minus 2, so it switches from negative to positive. And it's negative to positive because it's coefficient 1 in front of the x, which is positive. So these guys are all the signs of these. So just as an example, this represents the sign of x plus 2 on the interval -2 to -1. That's what this is representing. So now what have I got to do? Well, I know my expression up here is a product and quotient of all of these. And if I have a bunch of expressions and I'm taking products and quotients of them, I can determine the sign by looking at how many negative terms there are. The positive terms aren't going to affect anything, but the negative terms could do. So if I have an even number of negative terms, that has to give rise to a positive value. So here in this first column, for example, where am I? In this first column, I've got negative, positive, positive, negative. I'm adding and multiplying these. The negatives are going to cancel. It has to be positive overall. So up here, bingo, I'm positive. Next, negative and 3 positives. That has to be negative. Next, 4 positives, of course you're positive. Next, 4 positives, of course you're positive. Fantastic. So what do these represent? These represent the sign of your expression. This is the sign information of the expression above. It's telling you the sign of this expression. So this is a really good way to do this, right? If you are able, and I'm stressing if you are able here, if you are able to take your expression and write it as a product and quotient of simple expressions, this is a superb way to do things. If you can't write your expression as a product and quotient of simple expressions, that's going to have to wait until you do more sophisticated mathematics and calculus. But there will be a method there which will work. But this is an important method to understand. It's a very good test of your kind of algebraic skills. So that's the reason I've gone through it so carefully. So yeah, this is a really excellent way of writing down sign analysis. It means you don't have to go by hand through every single potential and work out which ones kind of match up. It gives you a pretty nice system for doing it. So maybe at the bottom I should say that the fourth step is what I've kind of just done really. So the fourth step is exactly as I've described, an even number of negatives in a column implies the expression is positive. Because an even number of negatives multiplied or divided, doesn't matter, is always positive. Similarly, an odd number of negatives in a column implies the expression is negative. So we've really done 3 and 4 here. So just to reiterate, there's an odd number of negatives here. That's why it's negative on top. There's an even number of negatives here. That's why it's a positive on top. So this is an important skill. We're going to see it's extremely important later on for determining things called domains of functions.